I would like to tell you something about alternative gravity conditions. The term is inspired by my summer school in ISA Academy in Belgium. If you have any question, feel free to interrupt me. The first question, what we need to answer is, what is gravity? We would like to tell about alternative gravity condition. In science, we have four fundamental forces of nature: electromagnetism, weak nuclear, strong nuclear, and gravity. Almost every one except of gravity is conducted to atoms, electric field, or stuff like this. But we have gravity. And what is important? Almost every stuff in universe create gravity force. We create gravity. Earth creates gravity force. Everyone stuff can create gravity. It's conducted. It depends of mass of two objects and distance between them. And it's like something we can see gravity from ourselves because it's very big. G constant, gravity constant is like 6.7 multiplied to 10 to minus 11. So it's very big. We don't have a very big mass. And what we can call like alternative gravity. Alternative gravity is everything what is no normal gravity. In Earth, we say that normal gravity is 9.81 or something like this. We can have hypergravity when we have above 10 meter multiplied by divided by second square. And we have microgravity. Microgravity is when we have weightless condition. We can have microgravity when we have conduction of free fall. We can achieve it almost every material. For example, lift. If we have a lift and if we assume that we don't consider air resistance and another stuff, and we have only gravity force, inside we have weightless condition. And we say that we can say that we have microgravity when we have 1 multiplied by 10 to minus 6 or something like this. But we can never achieve 0G. 0G is something abstract. It's only something we can be very close, but we can achieve 0G. Because we can have, for example, 10 to minus 10, but it's still something. It's never 0, actually. And this is the lift, for example, where we can achieve. We have free fall inside. Also, if we throw a subject like ball, inside ball, if we assume that we don't have air resistance and another stuff, we have microgravity inside. Because we have only gravity force. It's what I say. The force of gravity is never negated. And it's not that we have lack of atmosphere present. We can have microgravity in atmosphere. A significant distance from Earth or any other mass is always something. It depends about if we have another force or high speed. We can have high speed with microgravity or low speed with microgravity. It is not what is called, what is necessary to achieve microgravity. And the most important fact for us and for science is how we can create microgravity. We have a few main ways how we can create. The most, maybe not popular, but the most famous is parabolic flight. When astronauts are training before a mission, and how it's going parabolic flight. And we have a very special aircraft, parabolic aircraft, but it's created in a special way because when we would like to create microgravity, we have like on the picture, we have parabolas. During one flight, we have usually 30 parabolas. Every parabola take around 1 minute. And between parabolas, we have 3 to 6 minute break. It's like we start at 6,000 meters with speed around 800 kilometers per hour. And we start to climb very high. We use degree almost 45 degree. Normal aircraft is 5, max 15, but it's very rare. So the aircraft need to be created with using better materials. And during this phase, we have 1.5 to 2G. We have hypergravity. After that, we have 20 seconds of 0G. Pilots turn off engines. We have only gravity force, and we have a parabola top. We have lower speed, and after this, we have hypergravity for 20 seconds, and we come back to 6,000 meters. On the top, we are like 8,050. It's very hard to create, and the pilots need to be the best, because if we don't create a good angle, we have something like this. If we have injection angle 42, we have gravity lever 0.16, but with higher duration. So sometimes, if you would like to check something, if another gravity lower than 1G, we can manipulate with injection angle. We can change gravity level and duration of each parabola. And usually, if we have research in using parabolic flight, is like we have campaign of 3 flights, and each flight 30 parabola. Usually, we can have 90 parabolas. If we apply for ESA to sponsor us, usually it's something like this, around 30. It depends from country, and ESA use one airfield in Bordeaux, in France. Second method how we can create microgravity is drop tower. This is the ZARN in Germany, is ESA drop tower. The idea is very simple. Inside, we have a cylinder. We have some box. When we can have a box or capsule, when we can put some stuff, and we create vacuum inside drop tower. It's the most time-consuming part, because it took a few hours to create vacuum, because the height of tower is over 100 meters, and we have free fall inside, and we have 2 modules. We can have drop mode that we go only down, or catapult mode, go down and up. And it depends about mode. We can have 5 or 10 seconds of microgravity. But the problem is we have a very small parameter, a very small size of our capsule. Diameter is the max diameter is 0.8 meter, and length we can have 1.6 or 2.4 meters. I read about some experiments about polymerization of material inside drop tower. Because if we have material, we can have a very different time duration of polymerization. We can use some material with very short time, for example, 2 seconds, and we can check how polymerization can take place in microgravity. Usually we have better specifics of materials after microgravity. And RPM. RPM is probably the most popular, but we have a lot of problems with RPM. In RPM, we can use almost only biological stuff like cells, plants, and we can create microgravity, but it's simulated microgravity. It's not real microgravity. It's like we have three axes of random, but we have microgravity because when we zoom vector from each axis, we have zero, but the gravity is still inside. And if we use stuff like dust, fluids, it will go every time down. So it's only for cells or plants, eventually some animals, if you would like to check. But it's very cheap. It's have a very long duration because we can check something for 3 months or 1 year. It's possible, and we have a very range of size what we need to test and what we would like to check. It's possible, but it's not the real microgravity. Space Rider is like we can send something to space, and we can put some cubes inside, and we can have experiments. For example, Space Rider is machine. It's a vehicle to take some stuff from Earth to orbit, and it should spend around 2 or 3 months on orbit, and you can put something inside, but every team has only one unit. One unit is 10 centimeter, 10 centimeter, 10 centimeter in every dimension. And ISS, probably the most famous. But even in ISS, we don't have equal 0G. It's like 10 to minus 6, minus 7, because we have mass of ISS, would create her own gravity. One of the last, how we can create 0G is magnetic levitation. We use magnetic field to put something inside. But it's very rare, very complicated, and only for animal and cells. But it's short time, only the max is 6 hours or something like that. But it's the same with RPM. It's only simulated microgravity, not real. Because how you can create a hypergravity? Hypergravity, usually we use a centrifuge. This centrifuge can create a hypergravity to 20G, and we have 6 boxes, and we can have another hypergravity in every one box. What is good for us? Because we can test in a few conditions in one time. What we have a problem with microgravity and how we can live in space, because it's conducted to all what I said. First is blood circulation. On the Earth, the most a lot of blood we have on our leg. But in microgravity, it's like we have much more blood in our head, in our up part, because our vessel and our circulation system is created to push blood higher, 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 because to fight with gravity. In microgravity, we the same system fight, but we don't have gravity. So they push our blood higher, higher, higher. And after, when we come back to Earth, we have lower blood in our head and in our body, because this mechanism can go lazy, can be lazy, can start can stop fighting with gravity because they don't have. It was weaker than before, and we lost blood during gravity condition. We lose water in our body, something around 2 or 3 liters. We have reduction in heart volume, decrease in cardiac output. Total fluid is 1 or 2 liters, and we reduce plasma volume in our blood, so it's not good, and it increases hematopoietic level. It's how many erythrocytes we have in our blood. It's all what can go wrong if you are in space a lot period of time. Kidney are going wrong. Almost 30% of astronauts have kidney stones. And a lot of astronauts lost vision after a few months. They need to use glasses. Before mission, they didn't need to. After, they need. And also, we lose bone density, but about it later. And of course, hydration and another stuff. Very interesting is vestibular system, because we have 2 parts. For example, Otilis, on the top, is about to read gravitation or linear acceleration. The second is circular part. Is created to check angle when you are and where is your body. And inside microgravity, the upper part doesn't work. And we have a lot of motion sickness because we have an image from eye and image from vestibular system go to brain and is created where you are, but the lips create the wrong image. So we have 2 impulses from eye and from vestibular system, which are not the same impulse. And create your eye thought that you are in another place, and your vestibular system thought that you are in another place. It's a lot of it's a very big problem for astronauts, and some people thought that we can fight with this using GVS simulation to blink a vestibular system and to create something that our brain couldn't read, vestibular system impulse. And immunological system. It's a photo of fruit flies. It was tested on fruit fly how our immunological system of fruit fly is very simple but it's very common to our immunological system. And sometimes ago they launch fruit flies to ISS, and they go back on the Earth and compare fruit flies from Earth and fruit eyes from IC, and they discovered that fruit flies from ISS which live in microgravity have problem to fight with some disease, like not with bacteria, but with some infection, some organ. Nice. And what I mentioned before, we have problem with bone density and with muscles. We lost something between 10 to 20% of muscle when we are in space, in microgravity, and we lost bone density 1 to 2% per month. In normal condition, we lose 0.5 to 1% per year, but only when we are older. But if you are in microgravity, it's all the same time. Always you will lose your bone density, and you can't fight with this. You can fight with muscle loss. It's like you need to train a lot of to have opportunity to don't lose your muscle density, muscle mass. Microgravity is almost always bad for our health, but artificial gravity in medicine is usually using hypergravity, which is very good for us. For example, this from Uruguay, probably. They tested gravitation therapy on person. It's after a few sessions, they can have legs, hands, and they didn't see any negative effect for people. What did they test? And it's that's what I would like to say. Almost every one of you heard about Superman. In original comics, they can't fly. They can jump very high because on Krypton we had a very high hypergravity. And scientists would like to create a small village to check how hypergravity is going to on our body, because we know that we have more muscles, we have better density of bones in hypergravity, and we would like to check if it's possible to help people in hypergravity. Reference, and thank you for your attention.
Thank you very much. That mention about Superman is on time because there is a new trailer for Superman movie, so we can all in this holiday time watch it. And thank you very much, Wojciech, for your presentation.
Have you got any question?
I have a question. Do you know anything about some updates of Vast company who is developing artificial intelligence? Artificial intelligence, but artificial gravity stations. Do you know something about it?
No, unfortunately, no.
Okay, thanks.
And we have a question from Krzysztof.
Okay, thank you very much for the presentation. Quite interesting. I have one comment and maybe one question. First of all, the comment. You said that during the parabolic flight, the pilots turned the engine off during this 20-second zero-G phase. Actually, they just idle the engines, so the shaft speed is at the lowest possible level, because turning on engine after it's off in the flight, it's first quite dangerous, and second, it takes a lot of time to start the engine in flight, so it's only idling. And my question or suggestion is, because the problem for astronauts is zero-G and loss of muscles and bones during long flights. There are ideas like how to create artificial gravity on space stations. So it's like rotating station, Space Odyssey 2001, very beautiful picture with very fantastic music. Have you tried or thought about very basic calculations, how strong such structure must be to produce at least partial gravity, like 30% of our gravity?
No, but when I was in ISA Academy, it was like it was a lot of engineer about microgravity and about ICs, and they don't have. I didn't have one opinion. They still discuss about what about microgravity. Would like to create it on another or no?
Yeah, but if you look at ideas like going to Mars and having astronauts in zero-G for 2 years, they probably won't be able to land on Mars because their bones will just simply break during the landing.
Yes.
So creation of artificial gravity is simply speaking a must. So looking at technical side of this problem, we should design the ship so that such gravity could be created, and it means that some parts of the ship will be at high stress. So the question is how big stresses are expected, and is it possible to create such environment, even to create partial gravity? So my recommendation would be for somebody doing mechanical studies to do very basic calculations, what values we are talking about, how big, how fast does it need to rotate, how big stress it creates in the structure, if it is very simple structure that you can imagine, so that we could get feeling what size is of the problem. So that's my recommendation for future.
Okay.
Thank you.
Yeah. And I see that Alexandra asked about psychological issue caused by microgravity. It's hard to say because you have a lot of things. You have isolation, don't good food. I don't know if you have ever eat food, constant food from 2 weeks when you usually use not fresh food, not meat, but you use some, I think, what you can create. You have everything mixed. It's not good for your physiological status. So we don't have something like now would clearly say that microgravity is bad for our physiological or mental status, but it's like you are a lot of stress and going to microgravity is not good for mental health.
Do we have any more questions? Questions are also welcome in chat, so you can ask them there.
And what about you, Krzysztof said, some engineer during academy said that if we won't create artificial gravity, it's like we break a human law, because it's the same thing. What we need food, we need to oxygen, and we need to gravity. So it's one of the most important things for human.
And water.
Yes, it's like for the most important stuff for people. Yes, Powder? If I understood you correctly, we don't need to create microgravity in ISS because we have microgravity due to the distance, and due to not only the distance, but the fact that we have only gravitation force. We don't use engine, we don't use anything. We have vacuum, so we don't have air resist. We have only gravitation force. So inside we have microgravity. It's like a free fall, but gravitation force is really small on the gravity. It's a hard question. A lot of people thought how we can create. We can use something like a centrifuge, but it could be what Krzysztof said, a very power consuming.
Maybe not power, but the strength of the station, because you will have high loads, centrifugal loads acting on the station. For example, ISS is breaking out now, so it cannot use that rotation to create gravity, but it should be probably designed specially for such condition. And of course, it will require certain energy to accelerate or slow it down. But I think the main problem is mechanical, not the propulsion.
And usually, when we use in space something to rotate, we don't need a lot of power, because we don't need a lot of speed. They said me that if we would like to, we have a lot of time in space, so we usually use a very small power to create, to rotate something, but we need to have a very higher speed of rotation, and it's not easy to create and to have everything.
It's a matter of quite simple calculations to show how fast do we need to rotate to get certain level of gravity, and from that point we can start thinking about other issues to resolve, like power, like strength of the design, and so on.
Okay, so any more questions, or we can close our meeting? Last chance. Okay, so I don't see any hands and comments. So thank you again, Wojciech, for your presentation. It was the third space webinar prepared by UNIVERSEH Local Team at AGH University. There will be more after holidays. So thank you again, all. Thank you for your questions, and happy holidays and happy new year.